Okay, let's look at the intermediate value theorem. Intermediate value theorem is a real fancy way of saying that you might have an x-intercept on a function. In this case, the first criteria is the function must be continuous. So all the functions we'll look at will be continuous. But notice in this first example, we have a fourth degree polynomial, which is fourth degree polynomials are all continuous. So we don't need to really worry about it not being continuous. The second thing says if you have two x values that are in the domain of f, and f of a and f of b are of opposite signs. So that means one is positive and one is negative. So in this case, f of a is negative and f of b is positive. So since a and b are of opposite signs and a is less than b, then there is at least one zero between a and b, meaning there's one x-intercept in between this positive function value and this negative function value. So we will have at least one root in between a and b. You might have more than one, but the intermediate value theorem just guarantees one. Obviously, if the function is not continuous, we could have something like a function moving along like this, very happy, and then there could be a hole here, and then it could go up here. Notice that I've just drawn in this hole, so the function is no longer continuous, even though f of b was positive and f of a was negative. There's a hole here, so the function is not guaranteed that there is an x-intercept in between those two. But it failed the intermediate value theorem because the function wasn't considered continuous. So since it's not continuous, then therefore you can't use the intermediate value theorem. But again, that's just a function that I made up. So I'm just going to erase that so we don't get confused. Okay, so first off, obviously this function is continuous. Let's take a look at this function on this interval from -1 to 0. Let's look at f of -1 and f of 0 and see if they're about opposite signs. And if they are, we'll conclude that there is an x-intercept in between those two. So here's the wrong graph. Here's the correct graph. So here's the fourth degree polynomial. I don't know why all these extra parentheses are written in there, but they are. Notice that we have a and b, where f of -1 is -6 and f of 0 is 2. So if you look back at our function, we're looking on the interval from -1 to 0. So -1 is -6 and 0 is 2. Well, notice my two function values are the opposite. One is positive and one is negative. According to the intermediate value theorem, provided this function is continuous. Well, it's continuous even though it goes down off my screen here. It's a fourth degree polynomial. All polynomials are continuous. So it goes down and it just comes back up. We just can't see that. Since this one is positive and f of -1 is negative, there is at least one x-intercept in between these two x values. I don't really care what this x-intercept value is. That's not what the intermediate value theorem says. It just says you have at least one x-intercept in between these two values right here. So let's take a look at how you would find those x-intercepts. So first off, let me turn on the calculator. Sometimes it's a little slow. This is a cheap version. So here's my polynomial function that I've already typed in for you. And so therefore we're going to use the table, let's go to first table set and make sure that we're on ask and auto. I want independent to be asked because we're going to plug in specific values. And it looks like I already did it. Nope, these are two different values. So here's -1, which is -6, and here's 0, which is 2. So my two function values are -1 and f of 0 is 2. So let's write that down. F of -1 is -6 and f of 0 is equal to 2. So let's write out what we need to write here. So we've established that this one is negative and this one is positive, and it is a continuous function. So we know that there's going to be at least one intercept in between a and b, not including a and b. So to write this out, you kind of have to write a little paragraph or at least really run on a long sentence. So since f of x is, what's the first part? Continuous. And f of -1 is equal to -6, which is less than 0. And f of 0 is equal to 2, which is positive. Then, by the intermediate value theorem, we are guaranteed at least one 0 on the open interval -1, 0. So notice I put parentheses there because the x-intercept is going to be in between those two, and that makes sense because if this is negative and that's positive, well, neither one of those is 0. So it has to be in between these two x values here. Apparently I spelled guaranteed wrong, so I just fixed that. So let's move on to the next function. So here's our polynomial function again, which is a continuous function. We want to determine what f of -5 is and what f of -3 is. So let's look at our graph of our function. Again, it's a continuous function. It's a polynomial. It's 3x cubed, which is a polynomial, which is continuous. We have two function values. F of -3 is -42.4 and f of -5 is -318.0. Notice that both of these have the same sign, so that means the intermediate value theorem doesn't guarantee that there's an x-intercept in between those two. There might be an x-intercept. In this case, we know there isn't one. But if we didn't know anything about the polynomial function, the function could go up like this, could cross the x-axis and come back down. So we would have an x-intercept. However, the intermediate value theorem only guarantees you an x-intercept or a 0 if the function values are opposite. And since here my function values are the same, the intermediate value theorem fails. So we just need to write that out in our little discussion here. So let's use the graphing calculator again. I think I already plugged in. No, I didn't. So let me pause here and write that in. So there's my function. Just make sure my independence on ask, my dependence on auto. I go to the table, I plug in -5 and -3, which is -42. I don't know why I had -42.4 before. So we'll just go with that. So -316 and -42. So since f of x is a continuous function and f of -5 equals -316, which is less than 0, and f of -3 equals -42, which is also less than 0, the intermediate value theorem does not guarantee a 0 on -5, -3. Okay, so there's just a counterexample to the intermediate value theorem. Our next problem is pretty straightforward. It says find k such that here's our polynomial function. We don't know what k is, it's some constant, and we know that x plus 1 is a factor of this. So since x plus 1 is a factor, we also know that if x plus 1 is set equal to 0, we get -1, so that means -1 would be a root. That means f of -1 must be equal to 0. So let's plug -1 into this function, set it equal to 0, and see if we can figure out what k is equal to. So f of -1 is -1 to the 4th minus k times -1 cubed plus k -1 squared plus 1. So we get 1, and this would be plus k plus 1 is equal to 0. So I get 2k, we'll just make this plus 2 equals 0. So 2k is -2, k equals -1. So that would be our value of k to make it such that x plus 1 is a factor or -1 is a root of this polynomial function. Our next question is, what is the remainder when x plus 1 is divided into this? We could do we could do long division. We could do x plus 1 is divided into -3x to the 17th plus 0x to the 16th plus 0x to the 15th plus 0x to the 10th plus x to the 9th plus 0x to the 8th, 0x to the 7th, 0x to the 6th minus x to the 5th plus, you get the picture. That's really obnoxious. So I would never use long division to determine this solution. Following that same logic, we could do synthetic division and get -3 and then 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. and do synthetic division with that, which would be really obnoxious. Probably the quickest way is to find the remainder using the remainder theorem, which says if you plug -1 into this function, you'll determine what the remainder is. So if we just plug -1 in, we get -3 to the -1 to the 17th, plus -1 to the 9th, plus, excuse me, that's a negative, so let me pause that. -1 to the 5th, plus 2 times -1. So this is just going to be -3 times -1 plus -1 minus -1 minus 2. So that's equal to 3 minus 1 plus 1 minus 2, which that gives me those two are 0, so that's just equal to 1. And my last one is 2/3 is 0 of the following polynomial function. There's a couple different ways we could do it. First thing we could do is we could plug in 2/3 and see what we get. Let's take a look at that with the calculator. So here's our function, x to the 7th plus 6x5, got that right. So we want to know if 2/3 is a root, so we could let's get rid of those two. 2/3, if I plug in 2/3, I get -3.3178, excuse me, positive, so 3.3178. So the answer is no. Or we could have used the rational root theorem, which says the factors of p, which are the factors of the constant, plus or minus 1, plus or minus 2, and q is plus or minus 1. So I get plus or minus 1, plus or minus 2. These are our possible rational roots. And since 2/3 is not in this set, 2/3 is not a 0. And finally, we could do synthetic division with 2/3. 1, 0, 1, -1, 0, 0, 1, 2. This actually gets quite ugly. I actually did it, but it's just not worth doing. So there's 3 different ways that we could show that 2/3 is not a 0 of this function. Plugging in 2/3 using the remainder theorem or the factor theorem, using the rational root theorem to eliminate it, or we could use synthetic division, which ends up being quite unattractive. You get a remainder of 7256 over 2187. Ugly. Okay, that's the end of that. That's the end of that movie.